Okay, so we're going to do some graphs involving rates, and the first one we're going to do is we're going to graph the rate versus the concentration. And so how does the concentration of a reactant affect the rate of the reaction? So you already know something about this. You already know in a zero order, first order, and second order reaction, you have at least some basic idea of how that affects the rate of the reaction. If it's a zero order reaction, you know that the concentration does not have an effect on the rate of the reaction. If it's a first order reaction, then if you double the concentration, then you'll double the rate. In a second order reaction, if you double the concentration, you'll quadruple the rate because we're going to square the value of the concentration in the rate expression. And so just with that information, you ought to be able to kind of sketch in your mind what these graphs are going to look like. So we're going to graph the concentration on the x-axis, and we're going to graph the rate on the y-axis. So let's make up a little table that will help us populate some data, and then you'll see the graphs. All right, so for the first example, we're going to run a zero order reaction. And so in a zero order reaction, the rate is equal to, so our little experiment here is going to be reactant A converting into product B, just simple one-step process here. So rate equals K times the concentration of A raised to the power of 0. Okay, so to keep this really simple, we're going to just use a theoretical value of K. We'll just say that the rate constant K is equal to 1. So let's populate that in there. And we're going to just do some simple concentrations for concentration of A. So let's say that A has a concentration of 1 molar, 2 molar, and 3 molar. So in a zero order where A is raised to the 0 power, so if we replace this X here with 0, then we're going to take 1 raised to the 0, which is 1, 2 raised to the 0, which is 1, and 3 raised to the 0, which is also 1. Now, the rate is K times A, so K times A. 1 times 1 gives us 1 for the rate, 1 times 1 gives us 1 for the rate, 1 times 1 gives us 1 for the rate. And so the rate and the concentrations are not going to change. So as the concentration goes from 1 to 2 to 3, the rate stays at 1, 1, and 1. So concentration of 1, 2, 3, the rate stays at 1. And so if you plot a graph of the concentration versus the rate, and you get a horizontal line, then that is evidence of a zero order reaction. That's a zero order reaction graph if you're plotting concentration versus rate. So let's look at a first and second order reaction as well. And so in a first order reaction, the rate is equal to K times the concentration of A raised to the first power. And so this is going to be, in this case, a 1 there. And so again, we'll keep the theoretical value of K as 1, and we're going to use simple concentrations of 1 molar, 2 molar, and 3 molar. So if the concentration of A is 1, and 1 raised to the 1 would be 1, and then the rate constant K times 1 is going to be 1. That's going to be our rate for the first experiment. If the concentration of A is 2, then 2 raised to the first power is 2, and K times the concentration raised to the first power is 2, so 1 times 2 is 2, and then 3 raised to the first is 3, and 3 is our rate there. So in this case, as we plot our rate versus our concentration of A, they are 1, 1, 2, 2, 3, 3. And so when you plot that, you're going to get a graph that looks like that running through the origin. So this is a first order graph of the rate versus the concentration. And finally, let's look at a second order reaction. And so in a second order reaction, remember that the rate is equal to the rate constant times the concentration of the reactant raised to the second power. And so in this case, instead of a 1 being there, we'll have a 2 there. So let's go through the same drill. And so if the concentration of A is 1, 1 to the second power is 1. Concentration of A is 2, 2 to the second power is 4. Concentration of A is 3, 3 to the second power is 9. Okay? So the rate's going to be 1 times 1 is 1, 1 times 4 is 4, 1 times 9 is 9. 1, 4, and 9 as our rate when our concentrations are 1, 2, and 3. So concentrations are going to be 1, 2, and 3. And we'll say that's 2, 4, 6, 8, 10. So we're going to have 1, 1. We're going to have 2, 4. And we're going to have 3, 9. And so you can see that we have an exponential type curve increasing here. The higher the concentration, the higher the rate, because in this particular case, the second order reaction, every time we double the concentration, the rate quadruples. And so we're getting this rapidly increasing rate as we increase the concentration. So let's summarize these three real quick. If we are plotting concentration on the x and rate on the y, we have three possibilities. We can have a horizontal line, and that would be a zero order reaction. We can have positive slope running through the origin. That's going to be a first order reaction. And we can have a sweeping exponential growth, and that's going to be a second order reaction. All right, second set of data to run a graph on here that you need to look at is going to be a concentration versus time graph. Okay, so we're going to do this and look at a zero order, first order, and second order reaction as well. And so let's think about this for a second. For a zero order reaction, how does the concentration affect the rate of the reaction? We go back here for a zero order. How does the concentration affect the rate? Well, you see we have a horizontal line, so the concentration does not affect the rate. And so if the concentration does not affect the rate, the concentration here does not affect how fast or slow this reaction is occurring. And so as time progresses in the reaction, and as A is consumed and there's less A available, it doesn't matter that there's less A available. The rate is going to remain the same. And so what you're going to have in this graph is you're going to have a steady decrease of the reactant concentration as the reaction proceeds. It'll just be a constant decrease. And you can see with this, if you did a rise over a run on this graph, well, the rise is the change in concentration of A, and the run is time, and that is the definition of the rate. And so the slope of this is equal to the rate. If it's a zero order reaction, we'll get the rate based upon the slope. All right, so what if it was not zero order reaction? If it's a first order reaction, okay, if the concentration is high, we'll have a high rate. If the concentration is low, we'll have a low rate. So in this case, what's going to happen when the reaction begins and we have a lot of A, the concentration of A is high, we're going to have a relatively speaking high rate. And then as the reaction proceeds through time and the concentration of this reactant reduces, so it swings back that way, then the rate is going to slow down. And so if we plot that on this graph, so this is zero order. So when we start the reaction, we're going to have a relatively high rate, and then as the reaction proceeds, the rate's going to slow down because there's less reactant particles, the concentration is less. and the rate slows down. And so this is your plot for a first order reaction of concentration versus time. And then lastly, for a third order reaction, it's similar to this. Let's see if you can figure it out. The difference is when the rate's high, when the concentration is high, the rate's even faster because we have that exponential growth here. So at super high concentrations, we're going to have this line way up here at the top. Makes an exponential growth. So what happens on this graph is when our concentration is high, our initial rate is even faster. And so since our rate is really, really fast, our concentration of A decreases rapidly. So we have a very sharp drop initially on this graph. And our concentration of A decreases rapidly. And then as our concentration decreases, the rate slows down. And so that's your second order plot of concentration versus time. Now, how do you tell the difference between a first order and second order? Because if you only saw a graph that only had one of them on there, it may not be quite so easy to tell the difference, right? So, this is the first order, that's the zero order. But since we don't have the two to compare in the single graph, how could you tell which is which? Well, you can do that mathematically if you replot this. If you replot this graph, keeping time on the x, and instead of applying the concentration of A on the y, plot the inverse of the concentration on the y-axis, the second order graph turns into a straight line through the origin. Now, you're actually not expected to know this. It's not a requirement for you to know this for IB, but I just think it's nice to kind of take you to that next level to kind of see how mathematics will help us to identify the differentiate between the first and second order. That's what I was trying to say there. And so inversing the concentration on the y will give you a straight line at the second order. If you inverse it and it's a first order, then you don't get a straight line. You'll get a line that looks kind of like that. Okay, it's going to have a curve to it. So inverse in a first order reaction does not give you a straight line. It gives you a curve of that effect. Okay, so those are the two graphs that you are expected to be able, basically to sketch and kind of interpret and analyze, which is kind of what we just did. Okay, that's it.